Hello and welcome back to the Operations Research 2 course. This week we are going to continue to talk a little bit more about transportation problem, especially about how we may perform sensitivity analysis on that kind of problem. So let's start. We're going to look at three changes. The first one is changing the objective function coefficient of a non-basic variable. And the second one is changing the objective function coefficient of a basic variable. And the third one is increasing a single supply by delta and a single demand by delta as well. We're going to see how these changes or how much these changes can happen, each of these change can happen, such that our optimal solution that we've got before remains optimal. So for example, in the example of the power coin the previous week, we have got this optimal solution. And we are going to look at how much changes we can make such that this solution remains optimal. In the first type of change, we are going to change the Cij of a variable that is currently a non-basic variable. So if we look at the table, we know that these empty cells, like that and that one, they correspond to non-basic variable. What we're going to do here is that we're going to change one of the costs of this non-basic variable. In other words, we're going to change the value that you see in the small squares here, which is the cost from one supply point to one demand point. In this type of change, the U's and the V's, they are not affected. So if you recall the transportation simplex in step 3, you can see that when we calculate U and V, we use the Cij of a basic variable. It means that if we change the Cij of a non-basic variable, the U's and the V's, they are not affected. It means that they will be exactly the same like these values. So let's see an example here. In this example, we're going to change C11, which is currently $8. The question is, for what value of C11 does the current basis remain optimal? In other words, for what value of C11 does the solution here that we get remain optimal? The thing that you need to do is calculate or recalculate the C11 hat. Okay, remember that the ones with the hat means the coefficients of that variable in the row 0 of the table simplex, if you make an analogy of the simplex table. So this is the one with the hat is the coefficient of this variable in the simplex table. C11 without hat is the original cost transporting from supply point 1 to demand point 1. Okay, so we recalculate this. Remember, as I said before in the previous slide, U1 does not change, V1 does not change, and in fact, all U's and all V's does not change for this first type of change that we do here. So we just use U1 equals 0, V1 equals 6. But now you replace C11 with 8 plus delta because we would like to know for what value of this change does the current basis remain optimal. Okay, so you get that C11 hat equal minus 2 minus delta. Now recall from the step 4 in the transportation simplex algorithm, this BFS here is optimal if for all non-basic variables, their coefficient is less than or equal to 0 in the minimization case. Okay, so we say that, okay, we may change C11 as long as this value is still less than or equal to 0. So we may change C11 as long as C11 hat, which is minus 2 minus delta, is still less than or equals to 0. And then we move around the delta to the other side, we know that as long as the delta or the change is greater than or equals to -2, then our current solution remains optimal. In other words, if the C11 is greater than or equal to 6, the current basis remains optimal. So how do you get this 6? Well, the current cost is 8, and then the change that you make is you're allowed to make the change from -2, -1, 0, +1, +2, +3, and so on, because delta is greater than or equals to -2. It means that you can go down from the current value 8 to 6 at most. So the C11 can be 6, 7, 8, 9, 10, and so on, such that the current basis remains optimal. Now for the second type of change, we are going to change the cost Cij that corresponds to a variable that is a basic variable. So we are going to change one of these costs here that corresponds to a cell that has the value, which means that that variable is is a basic variable. In this case, the u's and the v's, they are affected because remember when we calculate the u and v, we depend on the Cij from the basic variable. So in this example, we are going to change C13. So this is the original C13, $10. And you can see X13 is a basic variable because the cell has a value. So it is a basic variable. Now the question is, for what value of C13 does the current basis remain optimal? So this is how we're going to change that. So from $10 to become 10 plus delta. Now remember that when we change the Cij for a basic variable, it means that the u's and the v's, they will change. Because again, when we calculate the u and v, they depend on the Cij of basic variable. So when we change the Cij of a basic variable, we need to recompute the u's and the v's. As always, start with u1 equals 0. And then from here, use the basic variable as usual. So now you can say that v2 equals 6 because 0 plus 6 equals 6. And then from here, you can calculate u3, which is equals 3 because 6 plus 3 equals 9. And then from here, you may calculate v4, which is equals 2. And then there's nothing else you can do. Now you can calculate v3. So v3 equals 10 plus delta. Do not forget the delta because 0 plus 10 plus delta equals 10 plus delta. Now use this basic variable to calculate u2. So u2 equals 3 minus delta because 10 plus delta plus 3 minus delta equals 13. Okay, so be careful when you have a delta. It can be something plus delta, it can be something minus delta. Okay, and then finally use this to calculate V1, which is 6 plus delta. Because 3 minus delta plus 3 minus delta plus 6 plus delta equals 9. Okay, so we have finished recomputing the u's and the v's. Again, as I said before, be careful with the deltas in the u's and the v's. The formula is still the same. ui plus vj must be equal to Cij. So for example here, 3 minus delta plus 6 plus delta equals 9. So now that we have recomputed all the u's and the v's, and it's like the step 3 in the transportation simplex problem, as usual, we go to step 4. In step 4, it says that we need to recompute the c hat for all non-basic variable. So the procedure is still the same. After you compute the u's and the v's, you go to step 4, which is checking for all non-basic variable. Again, non-basic variable. Calculate the c hat, the new c hat for all non-basic variables. And the formula is still the same. ui plus vj minus cij. So for example, the c11 hat is u1, which is 0, plus v1, which is 6 plus delta, minus 8. So you get delta minus 2. And then because the question is for what value of C13 does the current basis remain optimal, it means that if we want this solution remains optimal, we need to make sure that all C hat for all non-basic variables, they are less than or equal to 0. So you put this sign saying that for all non-basic variables, we want the C hat to be less than or equal to 0. And then you kind of simplify everything, move the delta to one side and the value to the other side. So you get this requirements in order to keep the current basis remain optimal. Then if we take the intersection of all these requirements, you will get that the intersection is from -2 up to +2. So the current basis will remain optimal if the delta is between -2. So the change means going down $2 up to going up $2. Since the current C13 equals $10, it means that if you go down $2, the cost becomes 8. If you go up $2, the cost becomes 12. So this says that as long as the cost of C13 is between 8 and 12, the current basis remains optimal. Now here what we're going to do is increasing both supply I and demand J by delta. And we're going to separate this change into two cases. The first one, if Xij, so the pair of supply I and demand J, is a basic variable. It's pretty easy if Xij is a basic variable. What we need to do is we just increase Xij by delta. For example, if we would like to increase S1, so this is S1 and D2 by 2 units, and we see that the intersection X12 is a basic variable. It has a value here. So what we need to do is just increase the value of the basic variable from 10 to become 12. Why 12? Because we say that we increase S1 and D2 by 2 units. And then based on this new optimal value, based on the new optimal solution, you may get the new optimal objective function value equals $122. Okay, so you may just multiply this 12 times 6, 45 times 9, 5 times 13, 10 times 9, 30 times 5. Now, if the Xij for supply I and demand J, in which we increase them by delta, and that Xij is a non-basic variable, then we need to do these steps. Okay, so let's look at an example to make this clear. Suppose we increase S1 and D1, and then we see that X11 is a non-basic variable. So the first thing that we need to do is find a loop involving Xij and some of the basic variables. So X11, that is X11, and then we create a loop involving basic variables only. So let's say we go there, and then we go down, and then we go to the left, because that's how we are going to create a loop. So now we have a loop involving xij itself, and the others are basic variables. And then find the odd cell in the loop that is in the row I. So because we are going to, because we talk about supply I, which is in the row 1, the odd cell in the loop that is in row I is that one, okay? This one. Because wherever we start, that is like the point 0 and 0 is even. So we find the even, odd, and then even, odd. And the odd cell in the row I is that one. We increase the value of this odd cell, which is in the row I, by delta. So our delta is 1 because we increase S1 by 1 unit and D1 also by 1 unit. So we increase that cell with +1. We go around the loop and then we will decrease that cell with -1, and then we will increase again that with +1. But we do nothing to xij itself. Okay, so let me repeat. So first you find the odd cells in the row I. So here, because our row I, the one that we changed is row 1. So you see that this is the only odd cell in the row 1. We increase that odd cell with delta. Our delta is +1. So this is +1, and then you go +1 -1 +1, and don't do anything to the original xij. So once you have done all that steps, you implement that. So here from 25 to becomes 26, from 5 becomes 4, and then 45 becomes 46, and do nothing to this cell. Now you can see that you have fulfilled the increase in the supply. Now this row becomes 36, and then this demand becomes 46, and then this solution is still the optimal BFS. Okay, the new optimal objective function value for this table, same as before, you may just calculate 10 times 6, 26 times 10, 46 times 9, 4 times 13, 10 times 9, and 30 times 5 to get this value. Okay, so that's how we perform sensitivity analysis in the transportation problem. Remember, for the third type of change, we need to separate whether the case is a basic variable or a non-basic variable. Okay, so that's for all the topics I'd like to talk about in the transportation problem. Next, we're going to go to another problem that is called the assignment problem. So see you on the next one, and thank you.